Welcome to Quantum Photonics. Dark matter, which makes up a significant portion of the universe's mass, remains unseen and undetected by conventional methods, and while its presence is indirectly observed through its gravitational effects, the exact nature of dark matter particles and their interactions with ordinary atoms are still unknown. The Quest-DMC project is focused on two primary candidates for dark matter. First, new particles with extremely weak interactions that have so far escaped detection, and actions, wave-like particles that are incredibly light. To capture these elusive particles, the team of our speaker today is developing a super-sensitive detector made from superfluid helium-3, cooled to near absolute zero. This detector, known as a bolometer, is enhanced with superconducting quantum amplifiers, making it capable of detecting even the faintest signal of dark matter interactions. The bolometer is designed to measure energy deposits that might result from dark matter particles colliding with the superfluid helium. Our guest speaker here today is Dr. Samuli Autti, who is a lecturer and an EPSRC Fellow at Lancaster University in the UK. He completed his PhD in low temperature laboratory in Finland in 2017, working on superfluid helium 3. Samuli was the receiver of the IUPAP Young Scientist Prize 2020 for a range of superfluid discoveries, and the 2023 Nicholas Curti Prize for his work on low temperature physics. In addition to dark matter work that he is presenting today, his work deals with the interfaces between classical and quantum physics, aiming to answer questions such as what does it feel like to touch a quantum fluid? And can we melt a time crystal? And if so, whether the outcome is a time liquid. So, without further ado, I proudly bring to you our special guest speaker, Dr. Samuli Autti. Samuli, welcome to Quantum Photonics.
Thank you very much, and thank you for the very kind introduction. Um, right, well, there was a pretty good summary of where we're coming from to today's presentation, but I thought I might still explain what are the kinds of things we know about dark matter, or why we believe that there is dark matter, and then from that move on to what has been done in order to detect it unsuccessfully so far, and then explain where we sit in this landscape and what we hope to do better than others have done before us. Now, there are some associated pictures, I think, in a PDF file which you can look at. But you don't need these. I'll try to explain everything so clearly that you don't need the pictures, but they might be interesting. So you may just as well have these things available. And on the first page, there is perhaps the most well known and certainly the most straightforward to explain observational evidence that we've got that refers to the existence of dark matter. Now, let's imagine we have a telescope, and we point this telescope at a galaxy. It can be, in principle, our own galaxy or some other galaxy. It doesn't matter. And then we follow the stars as they go around. We follow the stars as they go around the galaxy. Um, and so this way, at least in principle, we should be able to measure the velocity at which they are circulating around the center of the galaxy. And then equally, we can use the telescope for counting the amount of mass, so stars mostly, that there is in the visible parts of the galaxy. Now, in reality, both of these measurements might be more complicated, and indeed we might need to use several different techniques for determining the mass and the velocities. But well, at least to some level of thought experiments, this is more or less what's going on. And then with these two observational data sets, we can then compare the velocity with the amount of gravity we think we can account for in the galaxy. What turns out is that the stars are going around the galaxy center much faster than they should be able to do. That's to say, with the amount of gravity we believe is there, the stars should just fly out of the galaxy. Now, beyond this, and a few other observations of this sort, um, we entered the regime of speculation. So there are no well-established explanations that are supported by direct experimental evidence. But we might guess that, okay, so it looks like we are missing some gravity in our calculations. And perhaps this gravity is caused by some so far undetected type of matter which does not interact with light, thus we cannot see it with our telescope, but which does produce gravity. And this idea is called dark matter, unsurprisingly. And beyond the existence of this missing mass, there are many possibilities what it could be that is what kind of particles or maybe waves are responsible for these observations. But if we follow this explanation, then it turns out in the universe we need somewhere around 5 times the amount of dark matter that there is ordinary matter. Now, this velocity measurements are in the first large figure, and the composition of the universe is shown by this pie chart on the right. Now, well, there's also dark energy in that right figure, which has to do with how the universe is expanding. And indeed, this is another name for things that we don't really understand very well. But I won't be talking about dark energy today. Right. Now, let's move on from the idea that we are missing something to trying to come up with ideas as to where should we be searching for these potential undetected particles. Well, usually in physics, it's a good idea to look for solutions to major problems in our understanding, such that they solve more than one problem, or indeed, for example, emerge as a side effect, as for the case of dark matter, of solving some other outstanding problem we've got in our construction of physical theories. Now, there are two particularly famous explanations or types of speculation in this category. Maybe I'll start from the one which was mentioned later in the introduction. So if we look at the theory of the cores of atoms, this is called quantum chromodynamics. There is an outstanding problem there, which I won't be able to explain in detail today within the amount of time I've got. But solving this problem with a theoretical postulate, an assumption, happens to have a side effect of creating very, very light particles. And these particles were named by an American theoretical physicist called Frank Wilczek after an American washing powder. They're called axions. Now, axions are a great idea, but theoretically. However, detecting them is notoriously difficult. And here I need to correct one misunderstanding, which is that uh, in the group where I'm working, or rather the publicity work that we have been doing during this summer, indeed there is an Axiom project as a part of it. However, I'm not working on that thing, so I won't be talking about that too much today. Um, now, why is it so difficult to detect axions? Well, the basic problem is that these are particles so light that they behave like waves. And so then we need some kind of a resonator cavity, essentially, for detecting them. But, but it's very unlikely for them to interact with anything. And so then the cavity needs to be tuned to a very specific, very close vicinity of the right mass for these particles, the mass which we don't know. And so then it might take a decade to build an experiment like this and to run it for some time that matters. But then you to scan a different region, you need another decade maybe, and so this way it could well take hundreds of years to scan the possible range of axion masses. So experimentally, the prospect of finding axions is well, you need to be an optimist to work in that field. Um, However, it's not particularly much better in various other places that you might be looking at. Um, if we move on to page 2 in the PDF, there is a graph stolen from the Quantum magazine there. Axions are pointed out there is in this orange region. And what is basically shown here is that, well, from very simple constraints that we are probably not willing to abandon, very basic principles of physics, um, axions can be somewhere in the range of some let's say 40 to 45 orders of magnitude in mass. Now this is utterly enormous. And hence people have been looking at, well, axions, and then another particularly compelling region. Compelling because if we start to make the standard model of particle physics but more complete, meaning we include symmetries that seem to be broken by it, which could be unbroken in kind of a general description. Or if we try to unify gravity and quantum mechanics, then a popular way of doing this uh, has to do with string theories, and these naturally produce so-called supersymmetric particles, whose masses would fall in the range, which is called here WIMPs, so weakly interacting massive particles. However, here the news are not so good. Namely, they were supposed to be created by the particle accelerator in CERN, LHC, but nothing was found. Also, you may have heard of large dark matter detector projects, such as those where you put a large tank of some noble gas deep underground, let's say xenon, for example, and then you just wait there and carefully record every little blink of light and jump of heat in this several tons of xenon. And these things haven't found anything either so far. And so this has ruled out a large part of the red mass range, the WIMP mass range, at least for the kind of interaction likelihoods that people believed would be kind of most likely. All right. So what we have done is we have well ruled out, or at least made WIMPs kind of less likely, and well, people are actively looking for axions, but that might take forever. Um, and so, at least partially because of this, the character of dark matter surges, or the kind of focus, has shifted, at least to some extent, in the direction of not looking where you believe they must be, these dark matter particles, but rather looking in the places where you conveniently can with existing technology or technology that can be feasibly created by this kind of purposes. Now, that doesn't mean that there are no theoretical reasons to look in these regions. It's just that these reasons are not quite as central in the like speculative space of possible future physics that we might have. Where do our work sit here? Well, Quest, quantum enhanced superfluid technologies for dark matter and cosmology, is a collaboration in which we are looking at the very lower end of the WIMP range, or maybe even below that. So in the vicinity and possibly as far below the proton mass as we can. This is, if you talk in particle physics or energy units, if you like, this would be like 1 giga electron volt, or maybe below that. And well, why might we? Why? So if it turned out that dark matter really was in or is in that region, then theorists would certainly start looking in the following direction for explaining this finding. Namely, um, the visible universe seems to be made of just one type of matter, regular matter, not antimatter. While, well, typically one would start from the assumption that the young universe, after the Big Bang, right after it, consisted of both types uniformly. Now, this is a well-known problem in theoretical physics and cosmology. Now, I told you that there is some 5 times more dark matter in terms of mass. Well, if we then wildly, I would say, just assume that, well, let's say dark matter is all our antimatter, and that the numbers, or rather the total energies match, well, then the fact that we've got this amount of dark matter points in the direction that the if dark matter is our antimatter, the like mass should be of the order of the proton mass or neutron mass or whatever you like, so that this kind of near equality is not outrageous. So this might be a reason for us to look in this region. All right. Well, so that was kind of the background to like what we know about dark matter, we don't know about it, and why we are looking in the region. Beyond that, obviously, I'm a superfluid scientist, so if it turns out I can use helium-3 for looking in a particular region, a particular mass range, then that's the only one I can work on anyway. So personally, this is closer to an honest description of why this particular mass range. Let me look at my notes. All right. Well then, what are we actually doing? Right. Well, I told you that a typical dark matter detector is essentially a large mass which you monitor very, very carefully. And you hope that every now and then a dark matter particle collides with your mass. And so, or if nothing, if there are no collisions, at least you have ruled out certain interaction likelihoods in the region of sensitivity. Now, in our case, we take superfluid helium-3. So helium-3 is a rare isotope of helium. Helium-4 is the regular stuff with 2 neutrons that you put in balloons and so on. Helium-3 is in large quantities collected as a side product of making hydrogen bombs. And so there are two sources on the planet. These are the US, and at least used to be, and you used to be able to buy it also from Russia, and maybe not so much now. And so helium-3 is in many ways a complicated, quantum mechanically very interesting system. But for the purposes of detecting collisions with some unknown particles, it's particularly useful because when it turns into a superfluid at extremely low temperatures, uh, below 1 millikelvin, so a thousandth of a degree above absolute zero, um, and if you cool it down further than that, let's say to 100 microkelvin, then it becomes extremely sensitive to heat added to the system. So if you have a collision with an atom and then the heat gets distributed, the energy gets distributed to the whole container, it is very easy to measure this kind of changes. And so easy indeed that actually the target does not need to be weighing several tons. In our case, it's going to weigh less than a gram, so a million times smaller than the typical noble gas detectors that people have so far built. And this dramatically reduces another central aspect of detecting dark matter. Namely, if we take a piece of matter in a ground level laboratory, we will see a large number of collisions with particles generated by radioactive processes in the surrounding materials, and also secondary and tertiary and so on particles from cosmic ray impacts and collisions in the atmosphere and in the materials of the refrigerator and the lab walls and so on. And so while you might expect, let's say, one dark matter collision a month, for example, these what we call backgrounds will occur possibly hundreds of times per minute in our case, and then if you scale the target mass up a lot, then it might be a completely overwhelming amount of like a false positive, or at least distractions. So while these huge tanks, you need to put them in underground and make everything from extremely radio pure materials, we don't need to go underground to make relevant measurements. Eventually, it may be useful, but for the time being, we are not doing that. And we do need to understand radioactivity in the materials, but we don't need to change them. We just need to know what's there. That's one of the things we have been doing, and that's actually described in the research article that was, I think, linked to this event today. And so then, finally, if we manage to build it and it works for a long enough time, we will be able to tell, or we will either detect dark matter, or at least, well, more likely, tell that dark matter was not in a certain region that has not been accessed by any other experiment so far in the proton mass range of dark matter masses and below that. And we hope to do this by orders of magnitude, slightly depending on what kind of details of interaction we're talking about. And eventually, people are talking about building a bigger detector and moving it to a mine to reduce the backgrounds to make the performance even better, and so on. But this will possibly be needed in some relatively distant future, not for the present experiment that we are building. Um, we have already been running a prototype detector, and we know that the concepts they all work. And, now it's just a matter of getting the components together so the sensitivity is large enough or high enough for this kind of experiment. Well, before we start the conversation, which I'm looking forward to, I will probably still say that um, I started by saying that uh, we don't really know very much about dark matter. We see the gravitational effects. Well, basically, we see that something in our understanding of gravity in large scales, galaxies and galaxy clusters and so on, is not quite working by actually a large margin. But that's all we know, really. And so the dark matter has been the prevailing picture, or how to explain this, for decades. To the extent that if you read popular media or even listen to some parts of the physics community, they will tell you that this is a well-established fact. But the truth is that we don't have any direct experimental evidence for the existence of dark matter. And it may well be, I mean, at least in principle, that this is not the right approach, and dark matter actually doesn't exist. Which is kind of a, you know, a chilling message for building experiments that might take a decade to construct. And then it could be that there is actually nothing to be found in the end. And with that, maybe we open the conversation.
Thank you so much, Samuli. I would just like to reintroduce our guest speaker for the sake of resetting the room and for the benefit of those who just came in. So, Samuli Autti is a lecturer and EPSRC Fellow at the Lancaster University in the UK. He completed a PhD in low temperature laboratory in Finland in 2017, working on superfluid helium 3. Samuli was the receiver of the IUPAP Young Scientist Prize 2020 for a range of superfluid discoveries and the 2023 Nicholas Curti Prize for his work on low temperature physics. In addition to the dark matter work he is presenting today, his work deals with the interfaces between classical and quantum physics, aiming to answer questions such as what does it feel like to touch a quantum fluid? And can we melt a time crystal? And whether the outcome is a time liquid. So yeah, that's our speaker for you. And yeah, I would like to announce to the audience that we are opening the floor for questions. So those who would like to ask questions or seek some clarifications, you may raise your hand. We will bring you up the stage. And I also take this opportunity to welcome Frank, one of our regular co-moderators here in Quantum Photonics. So yeah, but first I'm very curious, and everyone, please refer to an article, a popular article rather, that I had posted here on the room chat from physics.org, actually, Samuli. And I would see in the picture that you and a collaborator are holding some equipment. Is that a bolometer? It said that the experiment is about 10,000 of a degree above absolute zero in a special
Mm-hmm.
refrigerator. So the first time I saw it, I was reminded of a quantum computer which they keep refrigerated. Can you tell us a little more about it?
Certainly. Um, So, well, that particular photo, if I'm guessing correctly, is we're mounting what we call the cell in our slang. But this is essentially the container in which the helium-3 is placed, and it is being connected to the refrigerator, at least most of the refrigerator, which provides the low temperatures. Now, um, well, it's maybe not shown in that figure, but I can briefly summarize how you achieve this kind of temperatures. Um, so we can in a research laboratory we can liquefy helium-4 with a large machine, and so with this liquid provides a stable starting temperature of around 4 Kelvin, so 4 degrees above absolute zero, which for our purposes is not very cold, but it enables us to start this like cascade of further cool down stages that go beyond that temperature. And then, well, there is uh, a system called a pot after that in a space which is thermally um, isolated from this bath, so which is in a kind of a vacuum container within the liquid helium-4 volume. And the idea of the pot is that you just reduce the pressure in there by a large pump, while slowly letting helium-4 in through some thin narrow tube, and this way the liquid in this pot cools down to about 1 Kelvin. And then beyond that, we take both helium-3 and helium-4, and essentially we mix them in another container in a chamber called mixing chamber. And this mixing process, if it's done continuously, can further reduce the temperature all the way down to a few millikelvin. And to facilitate continuous mixing, you need all sorts of sophisticated structures and tubes and pumps and so on, but we can skip that now. And then after a few millikelvin, there's only one more step, which is that we take a large amount of high purity copper, uh, which is actually inside of the thing I'm holding in that photo, and then we place it in a large magnetic field, and we cool it down to as low temperature as we have otherwise available, so that's a few millikelvin of the mixing chamber. And then we remove the connection one way or the other. In principle, for example, by just physically cutting it, but in practice it's a bit more involved than that. And we ramp the magnetic field down, and temperature then drops in the copper nuclei, and because of that also in the copper electrons and phonons. And it can be used for cooling anything else, including the superfluid itself, to very low temperature, which, well, in our case, the lowest we can achieve is probably a few, a notch below 100 microkelvin, so that's 100 millionths of a degree above absolute zero, or indeed 1/10,000th of a degree, if you like. So this is how we cool down superfluid helium. And then I was going to add on to that so you mentioned quantum computers, in particular these like superconducting architectures would be relevant here. Now these people, well, they don't maybe cool down all the way to microkelvin temperatures, but they do get to some tens of millikelvin, and it turns out the technology they use was, well, first of all, originally created for helium-3 research several decades ago. I know personally some of the people who were creating it. And the companies that you would buy a machine like this, like these days, for example, Oxford Instruments or Blue Force Cryogenics, or, as an example, these actually, for example, Blue Force was founded about 10 years ago by a guy who did his PhD in the same group where I did mine. He left when I was starting, essentially. And these machines, they are kind of a simplified version of what we are using. And so, well, one of my favorite stories about this is that when I was young and watching, I don't know, Star Wars, for example, I had this feeling that it had like makes no sense that some homemade kind of garage edition of a spaceship would be the fastest and the best and you name it, like the Millennium Falcon. and that was until I started working in a research lab, and I learned that this is exactly the way it works. Actually, so the guys making science fiction, they actually knew what they were doing. And for example, the best cryostats are entirely built in the labs, and they kind of contain all sorts of uh, homemade-ish details which you wouldn't find in a commercial product.
Yeah, thank you. Frank, in case you want to ask questions, just flash your mic. And hi, Eric. Welcome to the stage.
Hi.
Yeah, so I was telling Frank in case he wants to ask questions, just flash his mic. And yeah, if you want to ask questions, Eric, I'll give you the floor.
Oh, thank
Although I
you.
have
Yeah. Yeah. So I
questions,
was,
so
yeah. So my
go ahead.
question immediately is, so the you're like, I came from theoretical physics, then moved into biophysics, more applications. Interesting how a lot of the tools kind of translated, but I found myself having to kind of become an engineer at some point, which was kind of annoying, but there was no way around it. And then the whole kind of division of engineer, mathematician, physicist basically went away because everyone at the table basically knows everything about the problem. So I was curious if you could comment on your journey in that respect. Did you find some difficulties adjusting to that kind of Millennium Falcon, as you put it, which is a freaking awesome analogy, and that needs to go in a book. So if you don't do it, I might just steal it and quote you. So yeah.
That's all right. Um, um, well, I mean, if I look at the or think about the times when I was doing a PhD, um, I was definitely overwhelmed on several occasions, if not pretty much continuously, by the like spectrum of things that in experimental physics, at least, you need to handle confidently, or at least somehow, to be able to carry out the research. I mean, then from that kind of a student's perspective, there were these group leaders, professors who could go from uh, like like theory speech with a theorist to soldering things to writing computer programs to mechanical engineering of some like well, it was a rotating fridge that in Helsinki that I worked on, so that was kind of a complicated beast, um, and all of that like within a one day, if you wish. um, well then well, some time passed, and I mean, in some sense, I'm now myself in a position where I need to be able to do that, and the perspective has changed a bit. So now it's more like it's easy for me to handle all these things in the sense that I know how they work, and for me the work related to like figuring out something which maybe goes ever so slightly beyond what I have done before is kind of negligible. Um, and the thing which now is taxing is that I like if if I myself have to do all the practical work, then like the amount of like concentrating on not making trivial but important mistakes uh, is also mentally taxing on some sort of like very humane level. And if I have to do it, then I can't do the like high level stuff anymore during the same day.
Yeah, yeah, management. It becomes like a I like how
Yeah,
Obama put it. He said you have 300 binary choices in a day. After that, your brain turns to mush. Doesn't matter what
yeah,
the problem is, and so you
yeah.
can kind of get caught up in the bullshit. But I love that. I love the analogy of that, or not the analogy, but the description that you gave for the high performance model that looked like that. So that's really
Yeah.
really exciting. Yeah, yeah, that's a really good one. So I'm gonna write that down here. But anyone else, Cecile, please.
Yeah, so Frank, as I said, please just flash your mic if you have questions. In the meantime, I'd like to ask. Oh, go ahead, Frank. I give you the priority.
Yeah, thanks. So, yeah, uh, Samuli, it's a great sharing, and it's, I mean, research in this, it's I wouldn't say it's cold, like it's very cold up there, I assume. But it's also very, one glorifying in a way. It's I mean, dark matter. I mean, I forgot who said that. If you do theoretical, I mean, do physics, you always shall be doing the most challenging problems. So I forgot who. One of the famous, physicists said that. Anyway, I
Yes.
think this is the wholesome truth. I think. Yeah. So. I just wanted to take the opportunity. I mean, quite a precious one. That again, thanks for sharing your
No, no
precious
worries.
thoughts to the platform. The to understand better of the dark matter, which is myself. I understood there's the rotational curve of the and all other evidence that pointing to the more than I would say maybe the community has formed a consensus that a dark matter, the existence of dark matter, right? So of course there's also other amount or but I think it's a very uh, kind of already decided that there's also that's why we search for their uh, particle, the existence of particles, right? So and my question is that I would like to get clarified is the um, what do we know so far? Is it that the total did you mention that we know the total amount of mass it should be, but we don't know the granularity. It's I mean apparently the search covers a huge range. Is there some ways can any other means to help to kind of reduce the ambiguity? Say, may I just happened to hear another sharing, podcast sharing that proposing sending many cheap atomic clock into the space. So so supposing to be there's we already know some kind of distributions of dark matters, say more in the center of the galaxies, for example. Maybe I'm just saying that what I heard, and yeah. So I guess I babble on a lot, but yeah, I guess that's my first question. If you can
Yes.
shed
No,
some
I mean
light.
that's a very good question. And I think the honest answer is that we don't really know very much. Um, I can try to explain what we do know. So okay, there are like there are no observations on scales smaller than a galaxy um, that indicate that something is missing. And then there are a few different types of observations at scales larger than a galaxy or the size of a galaxy, as in the case of the rotation curves, that essentially they show that our current model is missing something. Um, and then uh, as we go get more distant from direct observations, then things like simulations of how the young universe evolves into being the present universe and that sort of things come into play. Um, and in these things, it's often useful to add some dark matter. Um, but well, I'm an experimentalist, so my kind of intuition based on my work on completely different systems, so like lab condensed matter systems, is that, well, if you have a complicated system, then like if your simulation of the complicated system is showing that I mean it doesn't match with the reality, that really doesn't tell you very much about reality. It just tells you that your model is not working. That's the experience in quantum metaphysics, and my like personal tendency would be to trust these few observations that we've got more than some like broad theoretical construction, until the point where the theoretical construction actually predicts some features that one can verify after the prediction, and then that's a different thing. But before we get to that, then like a theory is a very difficult kind of discipline. And in a cynical experimentalist might say something like, you know, to a first approximation, theorists never predict anything in complicated systems. You need to tell them what the right answer is, and then they will tell you, or they will force their or fudge their theory to produce this answer. Come up with the right sequences of assumptions, of how to use the model, how to use their complicated theory to produce the right answer. And then it might take a century to figure out why these were the right assumptions. But so what we've got is definitely our understanding of how gravity works in a galaxy scale isn't isn't explaining the observations. So either we are missing some mass, or our theory of gravity is wrong, or something like this. Now, I'm working on a dark matter project, so obviously I'm supposed to believe in dark matter, but there is, it should be said, also another community, which is, well, probably smaller, but it does exist, who are working on uh, ways of modifying gravity instead of postulating some new matter. And well, this opens an interesting possible answer to what, other than just trying to like blatantly observe dark matter collide with our some not so very sophisticated lump of matter we can produce on this planet. What else might you do? One answer is that, well, um, uh, if by no other, for no other reason than just like out of desperation, we might start looking for experimental observations where the dark matter and any alternatives that there are different. And increasingly in the past few years, at least in what I've been able to observe, uh, this really has started happening. So, as an example of something I recently encountered, I will not be able to judge whether this is reliable, but there is a published paper that came out a couple of months ago where people were measuring these, what we call rotation curves, far outside the visible parts of galaxies. So, well, you start with the red shifts and blue shifts of starlight to measure velocities, and then you move on to the red and blue shifts of emission lines from hydrogen and something like that to determine the velocities at which things are moving in their orbits around the galaxy. But then that comes to an end at some point. There is just nothing there to be seen. And this group, they took gravitational lensing as a way of measuring gravity. So when gravity bends space-time, then light moves differently through this part of space-time, and one can this kind of lensing effect can be used as a measure of the strength of gravity in general relativity. And so then, by some sort of statistical analysis of how the universe behind the galaxy they were studying was distorted, they were able to work out what the rotation curve would look like. Not tens of thousands or even 100,000, but up to a million parsecs um, outside of the galaxy center. And what they found was that this deviation from the expected decay to zero, which you would get for a distant point mass, never occurs. So this might be wrong. Their methods could be completely faulty. I cannot judge. But if they are correct, then this will change our understanding of what dark matter has to be like if this is the right way of explaining things. For the simple reason that the region which you need to populate with dark matter to account for this extra gravity is then very large and larger than we thought it could be, which could be even a problem for dark matter itself, and then, for example, might support some alternative ways of explaining things. So this kind of experiments looking for just improving the observations that we've already got is certainly one approach to narrowing down what we're looking for. Well, the other approach, what one can easily imagine, was already mentioned earlier. So okay, we've got these like theoretically motivated bands in the 45 orders of magnitude of potential mass for the dark matter. So the thing is that we don't know what the mass is. Well, maybe one should say that we don't even know whether it's just a single type of particle. So there could be several different masses and therefore reduced densities for each of them, and which makes things even more hopeless. But but we don't really know where to look. There are some bands where we believe looking is well motivated, but that doesn't really have to mean anything. Um, and so then what people have been doing is they have started looking not where they believe they're going to find something, because that didn't seem to work, but rather where they believe they're going to be able to make good measurements. And well, whether or not this is a good idea, I don't know, but certainly it's a different approach. Um, what else could be there?
Yes, so I think you talked a little bit about this a while ago, but and Eric IO has some comments and questions here at the room chat.
Yes.
But anyway, I also have some question, but I'd like to read at least the comment of Richard Feynman, who is who wrote something on the chat. What I mean by Richard Feynman is he's one of the listeners that we have now. So that's his
Mm-hmm.
Oh, I
alias.
thought he was an AI. You never know these days, right? Like AI Feynman got reincarnated in digital form. Who knows?
Yes, so Richard Feynman said, how can precise gravitational lensing measurements of galaxy clusters and strong lens systems be used to map the distribution of dark matter on the subgalactic scales and test alternative theories of gravity? So, if you have some additional comments, because I know that you already mentioned this a while ago.
Right. So um, on a scale of a single galaxy, this is a straightforward extension of the rotation curve idea, which I already explained. And I don't have much to say about beyond what I already said. Basically, you'd just be measuring whether this apparent density of dark matter actually persists beyond what we believe it should, much outside of the range of the visible galaxy. Now, galaxy clusters, then. Um, so these are a collections of galaxies that are held together by the mutual gravity, where things like collisions between galaxies can occur. The famous bullet cluster uh, collision is well, perhaps the most well-known example. Um, and so these are known to or at least thought to be good laboratories, not only because they are even larger than galaxies by a lot. So the faint discrepancies in our understanding of gravity are presumably more pronounced, but also because you can have dynamics of other sorts, not just going around some center of gravity, but for example, collisions between two centers of gravity, as I just described. This is what the bullet cluster collision was. And so then, well, yes, you have gravitational lensing between and within galaxy clusters. Um, And just like for a single galaxy, you can use that as a measure of local gravity. Now, I should probably say very clearly here that I don't know much about galaxy clusters myself. So this is kind of just based on a very superficial understanding now. But but um, based on already well-established observational material, I think it is very clear that galaxy clusters can be used for material, um, well, not only for simulations, but also narrowing down what is possible and what is not possible. Um, so improved observations um, are always useful, regardless of what they actually focus on. And maybe I could add on a kind of general level that as an experimentalist, as I perhaps already explained, my kind of default attitude is often that it is very unlikely that difficult physics problems get resolved uh, by theoretical efforts only. There are some counterexamples in the history of physics. General relativity, for example, comes to mind. But like the usual day-to-day experience in at least condensed matter systems is that you need good enough experiments, many experiments sometimes, and then things start to move, and it's quite possible to end up in a situation where there's an accumulating body of discrepancies in the experimental material, which persists without explanation for, humanly speaking, a fair amount of time. This is how quantum mechanics came about, for example. So it was well, I would say several decades of contradictory observations, um, and lack of understanding before quantum mechanics started to emerge, and then further decades before it was established into something that was at least remotely somehow systematic and useful.
Yeah, thank you. And Eric, can I just ask one question and I'll pass the mic to you? I know you have many
Yeah, yeah,
questions.
no problem. Of course, please go ahead.
Thank you. So, Samuli, the Quest DMC team has conducted extensive heat leak and radioactivity assays on various cryogenic materials. What
Mhm.
factors do you think are most critical in selecting materials for such an ultra-sensitive experiment, especially I think you're doing an underground operation?
We are planning one. Yes, we're not quite there yet, but some of the people working in the collaboration have been a part of another dark matter project, which is already underground, as far as I understand. So we've got some expertise in the team. What aspects are important? Well, on the level where our like current sensitivity is, the most important thing is that you avoid particularly bad materials. For example, if the materials you're using contain any potassium, say, then then that's a very bad idea. And let's say uh, let's assume we are using some composite materials, and some of them are reinforced by a glass structure and others are not. Then, because of the presence of the glass, so if you buy, for example, glass reinforced nylon, then that could be orders of magnitude more radioactive than just nylon or some structure without this kind of contamination or feature, if you like, uh, up to hundreds of thousands or millions of times more radioactivity. Um, well, then, uh, if we remove this kind of like massive screw up materials, what is left is relatively radio pure materials that one can use, um, and the end of the spectrum at this the most sophisticated end of the spectrum is where uh, like radioactivity, ambient radioactivity has been made as small as you can, and then you just can't get rid of the rest. This might be if you're using high purity materials that have been produced to the best quality that they can be, metals, copper, for example. Um, and then the rest you would shield away rather than try to remove. So you just place something that can absorb the products of radioactivity before they hit your target. And so there are some materials which are famous in this sport. Roman lead is probably the most famous one, I would guess. Which so lead is good because it's high density, so it's good for absorbing things flying through it. Um, this is basically just a game of adding enough protons in the way of neutrons. Um, and why Roman lead, and what does it even mean? Well, so basically, you hire a diver who in the Mediterranean who will dive to to the lead ballast of an ancient Roman ship and gather some lead from there. And the reason this is done is that this lead has been protected by the surrounding water for centuries, or well, possibly 2 millennia. Um, and so the level of radioactivity in lead has thus been reduced beyond what is possible in lead that is constantly being bombarded by other ambient processes if it's not under hundreds of meters of water. So Roman lead is then used as a shield in these things that go to some deep mines, such as Bowlby in the UK, or Grand Sasso, or several other places in Europe and the US, and globally. Um, ooh.
Yeah,
And
thank
then,
you.
of
Some
course,
very interesting.
maybe one more thing which I could say is that obviously the only thing you cannot shield is your target. So then the target, whether it is a noble gas or something else, that really needs to be basically atomically pure. And there are, luckily for noble gases, there are ways of achieving that relatively easily. For example, by feeding the gas through some cleaning system which contains lots and lots of surface area that's cold. So, for example, if we take simple charcoal and cool it down and feed the gas through this volume, then almost everything is captured by the charcoal, and out comes a highly purified gas. And then you may have to go a bit more sophisticated than that, but the idea remains the same.
Yeah, thank you, Samuli. So, I would just like to tell everyone that Samuli is our recurring speaker. He was a guest speaker probably more than a year ago. Samuli, was that? Yeah, I think
I
it was
don't even
still
remember. Is it 2 years, maybe
during the
even?
time of the pandemic because I remember you got sick and
The
even,
before
you know,
times. The before times, right?
oh my God. So, even if you were still sick and haven't recovered yet from COVID, you still, continued to have uh, the event with us. So, very, very professional. And I would also
I
like to
I think it
mention,
was I think it was summer 2022, according to my records.
yeah, I think so. And
Yeah.
of course, I would just like to mention that, we are very lucky to have Samuli here because of his experiment. And who knows, he might, really have a significant discovery and might be a Nobel Prize winner in the future. So please
Well, I
remember
mean,
this rule.
I mean,
Yeah.
I
Yeah,
would be
no
delighted
pressure,
to,
no
but
pressure.
well, I mean, I remember when we were writing the proposal for this project, and I mean, a part of the introduction was a couple of sentences along the lines of You know, should we discover dark matter that will transform physics forever? Um, but of course, the reality is that not only us, but in all the existing dark matter projects so far have only been able to tell us that dark matter was not where they could measure it with sensitive enough equipment. Um, so basically, every dark matter experiment is measuring backgrounds and explaining the backgrounds, and then when you explain the backgrounds, there's usually nothing, or always so far has been nothing left.
We're pretty sure
Uh,
our idea is nowhere here to be found at all.
uh, and of course, at some point, if this continues, then there has to be a conversation uh, about changing the strategy somehow. But yeah, I mean, so far it is definitely the kind of uh, prevailing picture for understanding what's going on in the universe.
Well, I
It's
think let's continue this conversation here, in the future for whatever you will find, because we had several rooms about Mond and also about some experiments in the Grand Sasso. So that's why I'm very keen about your experiment as well, because, yeah, it would lead to maybe, if not necessarily discover dark matter, maybe it would lead to also very important questions that we have to ask in science. So yeah, that's why it's very interesting. So, anyway, I'd like to welcome Kevin and Ash, who just came on stage. Welcome, Ash and Kevin. But just before that, I promised Eric that I'm going to give the mic to him. So,
yeah. I'll
uh,
take all my questions, make them into a simple one, and it's kind of more motivated by what just Simile just said now. And it's did you think of deploying like a hundred, maybe 200 meter like bubbles of water out into space as probes, and have that kind of be distributed? So as our star travels around the Milky Way, we could be deploying these kind of pylons along the way and get this distributed mesh. Is that something that you've considered? So I'll just keep it simple that, and then we can move on to some of the other folks.
Um, no, I haven't thought about that. Um, uh, it could be interesting to think about it, but I'd need a while to understand what might be the difficult parts there to say anything particularly relevant about it.
Yeah, because like the whole thing about like a water bubble kind of protecting or buffering your measurements, so you can actually take very precise measurements of things that are more strongly interacting with what you want, or the kind of interaction that you're wanting to see. So um, that's really exciting. But I'll just the questions that I wrote in the room. If you wanted to address one of them. Um, um, like for me, it's always a question of like materials. So like it would be like a very simple question, like the logistics, like the material that you chose. What was the price scaling to the next material? Like what was the range there? Was like the next best material like 200 times more expensive and therefore not feasible because it's brittle and breaks down? And so, like, which way did the scaling go for this kind of science?
Um, right. Well, for this particular type of detector, you really don't have any options. So, in terms of can we reach this sort of sensitivity to collisions in any other system, the answer is, at least for the time being, a no. And the simple reason is that we only know of two different superfluids, at least on this planet anyway, and these are helium 3 and helium 4. And well, helium 3 is a fermion, helium 4 is a boson, and they behave because of that in very different ways. And one of the consequences is that the typical energy scale for helium 3, typical temperature scale also, is much lower than in helium 4. Um, well, I might be able to explain why this is, but basically, um, for quantum a quantum system behave uniformly, so for the particles to go to the same quantum state, if you want at least a hand waving explanation, then they need to be bosons. Helium 3 atoms are fermions, they can't do that, and they will form pairs. So pairs of fermions are bosons. Now, in order to form pairs, you need an attractive interaction, and it's basically this attractive interaction is only detectable and has consequences if the system is really quiet. There are, well, I mean, there's no, like, almost no thermal energy to try to tear apart these paired helium-3 atoms, and that's why the characteristic, the natural temperature scale for the helium-3 superfluid is very low. And then the secondary consequence of all that is that helium-3 is much more sensitive to tiny energies than helium-4 would be. And then we have, that's all the superfluid systems we've got, and superfluidity itself is largely enhancing the consequences of an external collision. So while you might be able to go around that with some completely different approach, this approach where the material itself is amplifying the signal like massively by its natural properties, it isn't really going to work without superfluidity. Now, I think you also asked about the price range and how you would improve this, and is it limited by what? Well, helium-3 is not a particularly cheap choice. Well, the material itself is well.
For some, like the joke you made earlier from Russia was like, well, maybe not so much now anymore. And I was like, yep.
Well, yeah. So I think the price is something like $10,000 or whatever pounds, for that matter, per liter of normal temperature and pressure gas. And if you want a liter of liquid, which is more or less what the size of the containers is, that provides the circumstances for a tiny target of a fraction of a gram in the end, in the middle of that. So this is going to be, well, the order of several hundred liters of gas. And so we're talking about order of hundreds of thousands to $1 million just to buy the sample. So, which is to say, we can make it bigger, so that way we can make the experiment obviously more sensitive. But well, within reasonable research funding, we can't really increase the size that much. And the secondary thing is obviously that, well, the supply is also limited. So if we start buying enormous amounts, then, well, there is only so much you can buy, and then there won't be anything left. So the price will obviously also depend on that to some extent.
So you have to eat the tuna before it becomes extinct. Got it.
Well, I mean, to be honest, the price increase, I believe, was not related to research. The price increase started after the terrorist attacks 20 years ago, where the US at some point decided that they're going to build detectors for radioactive materials at border crossing points. And the technology they selected for this was helium-3 gas detectors, which are very useful, but it meant that they started using enormous amounts of helium-3 on the scale of usual consumption worldwide, and then the price went up very dramatically afterwards.
I see. Yeah, cool. Thank you.
All right. If there's time, later, Eric, we'll circle back to you again. In the meantime, we'd like to, and yeah, thanks for asking very interesting questions as usual, you and Frank. So, Kevin is here, and yeah, I'd like to give the mic to Kevin. Good morning, Kevin.
Oh yeah, I haven't had any caffeine yet, so but I should probably pass the mic to Ash while I do that. But since we're kind of speaking humorous, I was wondering if DMT has anything to do with this research, in interdisciplinary. I know you're also into interdisciplinary research, and then also, DMT could be a dark matter transhumanism training. That would be a Audi TT. My favorite car. So I don't know if you have anything to say about that. Well, I guess in caffeine.
You may have to translate DNT for me. I'm guessing this is some sort of American governmental institution, but I could be wrong.
It's a psychedelic experience that borders on the realm of understanding your own consciousness. It's a transcendental experience that some people have, and I guess that's the nature of the question, Kevin, that you're asking. The mysteries of consciousness, could they be related to this? Maybe that's an ancillary or generous interpretation.
Yeah, rather than DMC. Yeah.
All right. Right. Well, I don't think I have a particularly good response to that, but
Yeah. The main question was for interdisciplinary, for material science and engineering and physics, getting
totally.
them together.
Yeah.
Yeah, I shouldn't attempt jokes before caffeine. I'm sorry.
That's okay. Right. Well, I might start from a kind of a personal perspective. So I mean, I have a lab physics, superfluid physics background, and well, if I'm being honest with you, um, certainly one of the motivations for starting this project was that in order to use it as this kind of a tool, there's going to be loads of helium physics that we need to understand first, because we will be looking at sensitivity and energy range that has not really been pursued before, at least not in this form. Now, so that's certainly personally some sort of kind of interdisciplinarity that is very much in play, and I believe this applies to many of the on the superfluid side of things, of the people who have been working on this. Well, so then when it comes to the general kind of environment of let's say understanding, well, even if there is no dark matter observed, we have to understand the backgrounds, and do this in the context of low temperature physics. And there are some other major enterprises gaining loads of popular and public attention, such as, well, let's say, quantum computing, where it looks very likely that understanding similar sort of low temperature like uh, engineering, uh, and on the other hand, radioactivity and cosmic rays, and so put together is going to be a key aspect of well, if not the present, then close future research tasks. So this kind of interdisciplinarity is definitely there. What else might there be? Well, I think these are the key things. When we are planning, let's say if we're planning to put cryogenic technology to go to ultra low temperatures into a mine, say, then this other community of quantum computing is potentially also very interested in using this kind of facilities.
Thank you. So, yeah, we'd like to pass the mic to Ash.
Thank you, Cecile. Samuli, thank you for a wonderful presentation. I only have a couple of thoughts. One, wouldn't I mean, if dark matter kind of lumps together, the things, maybe we can't measure it from in it in a way. And I don't know what your thoughts on that, but and also, have you seen Yvette Fuentes' experiments, and what are your thoughts on, if anything, there? Give us a few hints on what we're looking at.
You may have to repeat the second question, but maybe I'll answer the first one first. So this question about dark matter forming structures, as I would probably formulate this in like a more general context. It's to some extent this is an open problem, or even largely, I would say. We do know that dark matter does not interact with ordinary matter particularly strongly. And we don't even know whether it interacts with ordinary matter in the first place, as we know it. Then whether or not dark matter forms structures, you can ask whether it forms structures on the scale, like large scale of galaxies, and then I think the answer has to be yes, because a uniform distribution of dark matter will not do. So you cannot explain, for example, these rotation curves with a uniform distribution, even if it is only kind of terminated somewhere outside of the galaxy. Because there doesn't seem to be much missing close to the center, most of this postulated missing mass is outside of the galaxy centers. So clearly you need some sort of large scale structure, but it could be that this is just established by gravity-related dynamics, so it might not tell you anything really about the interactions other than gravity. Well, then when it comes to smaller scale structures, at least some types of dark matter so dark matter which we cannot directly observe, that people have discussed, and or perhaps in the present, some of these ideas may have been discarded. But if I take an example, then small or primordial, if you like, black holes is something that people have discussed. So black holes small enough so that we could have some sort of abundance of them. We obviously wouldn't be able to see them directly, and they could form a part of this missing mass. These would very obviously have structure, and I wouldn't even call it lumping, I'm sure you're aware that black holes have extremely high concentrations of mass in them. But this kind of ideas, as far as I understand, have been discarded, not because they cannot be, for example, black holes like this, but because it seems that you won't be able to come up with a density high enough that is otherwise consistent with what we know about the galaxies and the universe, and probably in particular the history of the universe. And then could you maybe remind me about the second question, please?
The second question is about Yvette Fuertes' experiments on time dilation, measuring time dilation between Earth and satellites, and what are your thoughts if that helps us understand anything?
I have to say I'm not particularly well educated in what these experiments may have resulted in, but generally speaking, it is surprising how many useful experiments people have been able to recently suggest and maybe start building, and in some cases even carry out, that are local but still tell us something relevant that narrows down at least narrows down the range of possibilities when it comes to what dark matter can be or cannot be. And I'm sure measurements of GR effects, such as changes in how time is flowing, can certainly be this kind of contributions. Other examples I have maybe looked at in slightly more detail. Things like, well, okay, I mentioned this gravitational lensing for measuring the rotation curves. There are other measurements like this one can come up with, and that people have been trying to carry out in order to either prove or disqualify these modified gravity ideas. For example, you might send probes to orbit other bodies in our solar system, and I believe this has, to some extent, already been done, and then measuring acceleration or trajectories there into high precision, and this might tell us something about or put some bounds on whether or not modifying gravity in some way is consistent with observations. A more recent and well reported class of observations has to do with data from, I believe it's the Gaia project. I could be wrong here, but I think that's the source of data. Anyway, so some sort of observational data which has to do with motion of stars in this case, and so people have been looking at how so-called wide binary stars are moving. The idea being that the gravitational pull between very far apart stars that are still bound by gravity into pairs could be weak enough so that one can test these discrepancies of gravity on the scale of binary systems rather than the scale of galaxies. As I'm speaking, I'm not sure whether people have arrived at a consensus. So some people have claimed that it goes this way, and other people have claimed that it goes the other way in terms of what is the right explanation or what is the conclusion from these things. My feeling is that no conclusive evidence for modified gravity has been found there. And probably many other approaches. One thing which I would find particularly compelling myself, or at least entertaining, is one can test various sorts of quantum effects when it comes to gravity in lab experiments. And while that does not directly provide information about dark matter, should they find any discrepancy in our current gravity theory, that would just add potentially very useful information or contribution to the pile of things to consider when people are trying to build a better understanding.
Yeah, thank you, Samuli. So, well, I have a question. I know that we've been here for about an hour and 30 minutes. Usually we ask our guest speaker, how much more time do you have for us?
Yeah, I also
Well, I
have
don't
a
know,
question
20
here.
minutes?
Time.
Sorry.
No, I think we can go for another quarter an hour, 20 minutes, something like that.
Yeah, thank you. So I
All right.
have a question, but after Frank. Frank?
Oh, sure. Yeah, thanks, Cecile. Can you hear me okay? Because my
Yes.
I have a red bar constantly displaying. Okay, cool.
What time is it
I
now,
had to
Frank?
go. Hello? Yeah? What did you say?
What time is now? Is it now on your end?
Oh, it's I don't have I don't remember now. It's been a
Well,
while.
it's
It says
probably after midnight, I think.
so. I have been able to skim that the paper Cecile shared in the chat room. The from the device that you shared in the slides, what prevents you
So I roughly understood that that seems the lower temperature is advantageous. That the lower you get, the seems the more sensitive you can get. What prevents you to go even lower from the? I see the milli-K, to 80 milli-K on your figure.
80 microkelvin actually is what is
Microkelvin.
there, but yeah.
Yeah, milli-K.
Right.
Sorry, micro.
Well, yeah, this is a good question. So, all right, the cool down stage, which is this lump of copper that we are using as the final cool down workhorse, that cools down to much lower temperatures. If need be, it can be all the way down to well, below or less than a microkelvin. But then the real bottleneck is in connecting the liquid, the superfluid, to the cold refrigerant, and so the basic problem there is that well, there's no electric activity in the superfluid, so the communication needs to be via mechanical vibrations. So this is usually phonons, or on the superfluid side we call it quasiparticles, but it's mechanical anyway. So we have some collection of thermal excitations in the superfluid carried by these quasiparticles. So they distinguish broken pairs of the superfluid state, which are flying around in the superfluid. And then we need to suck that energy out across some metal liquid interface in the system. And in order to do this, the basic problem there is that the mechanical excitations in the superfluid are completely different, or very different in terms of the mass or the momentum they are carrying and the energy that they are carrying, as compared with the typical mechanical excitations in the metal. And so, as a consequence, then these two populations of mechanical excitation simply cannot exchange energy very efficiently, or well, almost at all. And well, what we can do is we can increase the contact area. That we can do something.
Hey, sorry, sir, I just missed the last very important sentence. Could you just repeat? You said there's because the two. Well, which two?
Oh yeah, so we've got a population of mechanical excitations in the superfluid, and then a collection of mechanical excitations in the metal. And we can cool the population in the metal, and then they need to talk to the population in the superfluid to cool that as well across the interface between the solid and the liquid. And because the properties of these excitations, in the superfluid we call them quasiparticles, in the metal we call them phonons, but all the same, their properties, so the energy and the momentum that they carry, are rather different on the two sides of the interface. Then they can't really talk to each other. It's very unlikely that you will that the superfluid quasiparticle will hit the interface and lose a lot of energy, and it turns into a phonon on the other side of the interface, which then can move into the metal and give the energy away further on to electrons or the nuclei, which are the coldest thing. And we can increase the contact area to maximize this exchange, and we do that by taking some powder of metal. Typically, this would be silver. So a powder with pore size of some tens of nanometers up to a micrometer, and then we compress this and heat it up a bit, and it melts into this porous metal surface layer, with an orders of magnitude higher surface area than what the plain metal surface would have. So this is how we do it in practice, but the limitation then is simply you do the best job you can with this kind of refrigeration, and the final temperature you can reach in the superfluid is given by the balance of this cool down construction versus the amount of heat which unavoidably enters your superfluid from the environment in the form of, well, radiation and possibly mechanical vibrations of the container, and furthermore possibly some sort of material like decay processes in the surrounding walls, and so on and so forth. And eventually, at this like 80 microkelvin or 100 microkelvin temperature, it's not known what the remaining heat is. It's very small, but we don't know how to remove it, and we don't know what it is. And this actually is an example of the kind of superfluid physics that we originally thought we might learn to understand, because one obvious guess would be that this is radiation from, well, radioactivity or cosmic rays or something else. And the particle physics expertise that we brought in for the purposes of understanding the dark matter measurements might also let us understand what the heat leak is and how to improve on that. Well, that's work in progress, and the answer is not conclusive yet. But that's essentially what sets the lower limit.
Yeah, I think this is quite interesting in a way that it's not just pure engineering, right? Because often that you're by breaking the limits. I understand. I mean, there's the lowest temperature that we can reach is in the pickle cave, but I mean, in your particular setup, there's for particular purpose, if you can manage to go even lower, you might, and even no new. I mean, I think there might be new physics, but you can also apply it to other valuable applications, right?
Yes.
Any
Well, I mean,
example?
well, obviously, I'm doing blue skies research, so I would be delighted if we could reach lower temperatures, just so I can look at new physical phenomena. Uh, uh, well, I can name some possibly Nobel Prize worth things in this context that we might be able to create should we be able to reach lower temperatures. But but um, perhaps I should emphasize that well, I mean, you will read about so and so temperature in some material, which could be, as you mentioned, picokelvin or well, at least nanokelvin in some cases, and so on. Now, um, temperature is a kind of a delicate, complicated thing in this range. I'll give you an example. So if we take our refrigerants, so not even the superfluid, but the copper piece that we're using as the workhorse for cooling down, um, at the temperatures that we're talking about, the nuclei of the copper, which are cooling down and as caused by the magnetic field change, will be at a temperature significantly lower than the electrons that they couple to. And then the phonons, these lattice vibrations of the metal, will be yet at a higher temperature than the electrons. And so this way, even in a simple system like a metal, there is really no well-defined temperature in the traditional sense of all the parts of the system actually sharing the same opinion about what the temperature is. So this is one thing. You should understand that at the limit of the lowest temperature you can reach, temperature becomes like badly defined in the usual sense of what temperature means. And then if you go even beyond that, excuse me, it's possible to for example, just cool the nuclei even further and forget about the electrons and the phonons, this has been done, and you can get the nuclei to picokelvins, as you said. It's actually the lab where I was working for my PhD in Helsinki, where I think this was done to the lowest temperatures anybody has achieved. And in some sense, this is kind of an interesting research project, but you cannot really hope to apply that temperature to anything else then at this limit. It's just your this single isolated subsystem that is decoupled from the rest of the world. And then, as kind of a tangential thought, there are also other exotic ways of cooling things. In particular, these Bose-Einstein condensates created from neutral atoms, let's say, which are suspended in some sort of optical traps in vacuum. They are often cooled down by just like conveniently releasing the fastest moving atoms from this kind of bottle in the middle of a vacuum container.
In vapor cooling.
Yes, and so then this way you can cool kind of a handful of atoms to also a very low temperature. And again, that comes, at least in most cases, at the expense of accepting that you're approaching, at least if not crossing, beyond a point where temperature, you need to really be rather careful with what that means. So in that case, you have a very small number of atoms, and temperature usually is defined for systems that contain so many atoms that you don't need to care about the numbers. But yeah.
Yeah, thanks. That's exciting.
So, Samuli, maybe I'll ask the last question. The Quest DMC project intersects several disciplines: quantum mechanics, cryogenics, and cosmology. What other interdisciplinary contributions could enhance the experiment, for instance? And yeah, for example, could advancements in artificial intelligence and machine learning improve data analysis or reduce the background noise?
I think, generally speaking, this kind of AI or neural network constructions have turned out to be very useful, a very useful toolbox, and um, it's quite possible that at some point this experiment gets going and the sensitivity is improved beyond, let's say, what we initially hoped to achieve, that we'll have such huge amounts of data containing lots of background events, for example, that it might be useful to apply this kind of tools just because of the sheer volume of the stuff gathered. As of now, I don't think we've got any plans, but that's, well, at least the first order, just because we can basically manually go through everything, and you can't really improve on that using a neural network model. The interdisciplinarity that one can, generally speaking, always hope to add is surprisingly difficult to, even if you know what you're looking for and what you want, and you have some resources to create this, to create like a conversation across disciplinary borders that actually works. In that it not only occurs on a regular basis, but also actually manages to overcome the differences in the ways of speaking about things that you will have in this kind of highly specialized communities, such as the dark matter community or the superfood community. So, I mean, obviously improving this conversation is something you can always hope to achieve, and hardly will ever be perfected. Um, I would guess if we had any other obvious uh, contributions to involve in mind, we would have already perceived that. So I'm not sure I can be able, I'll be able to suggest something that's relevant right here, right now. But on the other hand, it's certainly this like applying one field to solve problems in another field has been a theme. For example, in recent UK science funding, and so strongly encouraged by in that context. And for example, this kind of meetings to look for potential new approaches in that direction are organized on a regular basis. Um, so maybe something will come up.
Yeah, thank you so much, Samuli. Thank you for your presentation and for answering all kinds of questions.
Yeah,
So
you're
I could
welcome.
see you have very interesting questions actually when I introduced you. So I hope that in the future we can discuss these questions again in
Sure.
quantum photonics. Yeah. So it was fun to have you as our guest speaker. So
Hmm.
yeah, we'll invite you again next time. So as they say, everything good needs to come to an end at a certain point and start again. So we are going to close the room. I would like to thank you so much for answering all kinds of questions, and I'd like to pass the mic to you if you have some parting shots for us.
No, thank you for listening, and it was a pleasure.
Yeah, thanks, Samuli. Where's Darcel for the counting down?
Well, you know that, yeah, I would just like to address there was a question from Ash earlier, which I wasn't able to answer. Why don't we have as many rooms as before? It's because, yeah, I think because of the policy of Clubhouse, so when there has been a change, many of our moderators that, yeah, did not want to follow that policy. So and besides I got very busy with my work so I was launching another product, so it was kind of hard to really do the room. So yeah, we're stuck, and a lot of people went for vacation this summer. I think this is the most time that there were a lot of scientists also that I know that who really went all out on the vacation. So yeah, that's my response, Ash. So we had said there were people who were raising their hands, but unfortunately, we're going to close now. And Ash, you were about to speak. As you are on stage, please do.
Oh, yeah, no, thank you. I've just been missing the rooms, and no, it's understandably the summer. On the collaboration piece, I mean, I would, yeah, I'd love to see a cross collaboration of like a strong sport. Maybe I'm thinking like competing on an X Prize or something.
Hmm.
Yeah, it's great. So, well, actually, I have a stealth collaboration, which is similar to what they do in X Prize since the past few months. But, well, that's great. I think there are people here in Clubhouse who are doing these collaborations as well. So, very much welcome. So, yeah, Ash?
Yeah, I was just yeah. Obviously, this is obviously the community I would bring it up to, but yeah, it would be good to chat soon.
Great. So thank you so much, Ash, for your support from before and until now. Thank you for your contributions. And I'd like to thank Kevin, who's always here supporting us, and Frank, thank you also for being here. And of course, our guest speaker, Samuli, and everybody who's been in the room, thank you so much for supporting us. I could not mention all your names. So as Darcel and Bob aren't here today, who would like to lead the countdown? Do you want to lead the countdown, Frank or Kevin?
Oh man, I finally woke up and had a question about some things. I was a little less than micro Kelvin, 150. But I was going to ask about phase matching, for axiom and squeeze states. But you may have gone through that. It looks like we're closing. So and yeah, I don't think I should try the countdown either with these technical questions.
Would you like to lead the countdown now?
Okay, I'll try. Okay, so we're starting off with the great number of 6.
6.
Frank 5.
6.
Ash
5.
4.
5. Sorry, I only see 5.
Number
got
3 and
I'll do the quadro and the
Cecile. Oh, yeah.
Cecile,
Yeah,
2.
yeah, maybe. Yeah, speaking of out of phase, yeah, and good doctor, you're number 1.
1.
Yeah, thank you so much, Samuli.
Yeah, thanks everyone. Thanks, Samuli.
You have a
Thank
great
you.
night, and see you next time. And also, everyone,
All right, thank you.
see you in the next rooms. Thank you again.
All
Bye.
right, bye.